570 million years after the Big Bang, the universe was barely a toddler. Stars had just started switching on. Galaxies were barely sketching themselves into existence. And yet, sitting in the dark, fully formed, was a black hole already billions of times heavier than our Sun. Scientists had a model, a timeline, rules for how things grow. This object broke every single one. We're going to travel back to the edge of cosmic time, uncover the black hole that rewrote the universe's birth story, explore why the math says it shouldn't exist, and follow the evidence toward answers that are somehow even stranger than the mystery itself. If you enjoy the journey, subscribe and leave a like. It genuinely helps. Brace yourselves. We begin. 570 million years after the Big Bang, the universe had barely begun. To put that in perspective, the universe today is roughly 13.8 billion years old. 570 million years into that timeline is like the first few days of a human life. The cosmos was still raw, still forming, still figuring out its own rules. Gravity was pulling scattered gas clouds together. The first fragile galaxies were just beginning to take shape. Everything was young, thin, and chaotic, and somewhere in that infant universe, a black hole already existed with a mass 600 million times greater than our Sun. Pause on that. 600 million suns, packed into a single point. Already fully grown, already feeding, already reshaping the space around it. Scientists confirmed this through observations made with the James Webb Space Telescope, cross-checked against multiple wavelengths of light. This is confirmed. The object is real. The discovery didn't just surprise the astronomy community. It sent a visible ripple through it. Papers were rewritten, models were questioned, because according to everything scientists had built over decades of careful work, an object like this had no business existing at that moment in time. Here is why that matters on a gut level. Imagine waking up one morning and finding a fully grown oak tree in your backyard, roots deep, branches wide, covered in leaves. You planted a seed there 3 days ago. You know oak trees take decades to grow. You have never heard of one appearing in 72 hours. And yet, there it is. That is roughly what astronomers felt when they confirmed the age of this black hole. The standard understanding of how black holes grow depends on time. A lot of it. Black holes grow by pulling in surrounding gas and dust, compressing it into a superheated disk, and slowly converting that material into mass. It's a process measured in hundreds of millions, sometimes billions of years. There are speed limits baked into the physics. A black hole can only consume matter so fast before the energy it releases starts pushing the infalling gas away, essentially throttling its own growth. Scientists call this the Eddington limit, and it acts like a ceiling on how quickly any black hole can get bigger. Even feeding at the absolute maximum rate allowed by physics, a black hole starting from a stellar remnant would need well over 1 billion years to reach 600 million solar masses. The universe hadn't even reached 600 million years old yet when this one showed up already there. So either the physics we trust is incomplete, or something extraordinary happened in those first few 100 million years that we've never directly seen. Both possibilities are unsettling in their own way. What makes this discovery land even harder is the galaxy it lives in. The galaxy surrounding this black hole is smaller than the Milky Way, significantly smaller, and yet this black hole at its center is absurdly massive relative to everything around it. The black hole outweighs the galaxy's ability to explain it. It's like finding a grown elephant standing inside a house built for a dog. Every galaxy we've ever studied closely has a central black hole that seems to grow alongside the galaxy in a kind of locked partnership. The bigger the galaxy, the bigger the black hole. They co-evolve. They feed each other's growth over cosmic time. This object throws that relationship completely out the window. And this wasn't caught by accident. Scientists were hunting for exactly these kinds of extreme early objects, pushing Webb to its limits, scanning light that has traveled billions of light years to reach us. They found what they were looking for. That almost makes it worse. Because if one exists, there could be others. And the deeper question, the one that keeps researchers up at night, is how the universe produced this thing at all. To answer that, we have to go back, all the way back, to the first moments after the Big Bang, when the entire cosmos was nothing but heat, pressure, and an impenetrable fog of energy. What came out of that fog, and when, is the key to everything. Numbers in astronomy usually feel safe to ignore. They're too big, too abstract, too disconnected from anything you can hold or feel. But this one is worth sitting with. 600 million solar masses. That is the confirmed minimum mass of this black hole. Our sun is already enormous, wide enough to fit 1,300,000 Earths inside it. Now multiply that sun by 600 million. Stack those suns together. That is the mass we are talking about, all collapsed into a region of space so small that light itself cannot escape it. For comparison, the black hole at the center of our own Milky Way, called Sagittarius A star, has a mass of roughly 4 million solar masses. It took billions of years to get there. The object we're discussing is 150 times more massive than our galaxy's central black hole, and it achieved that in a fraction of the time. That comparison isn't just dramatic, it's scientifically damning. Because our Milky Way is not a small or young galaxy. It has had billions of years of active feeding, mergers, and growth to build its central black hole up to 4 million solar masses. This ancient object hit 600 million in less than half that time, in a universe that had barely organized itself. To understand why that's so alarming, you need to understand the concept of the Eddington limit. Every black hole, as it pulls in surrounding gas, heats that gas to extreme temperatures. That heat generates radiation pressure, an outward push against the very material falling inward. At a certain feeding rate, the radiation pressure becomes strong enough to stop new material from falling in at all. That rate is the Eddington limit. It acts as a hard ceiling on growth speed. Think of it like trying to fill a bathtub through a faucet while someone keeps pushing water back up the drain with a fan. Feed too fast, and your own energy works against you. Even feeding at 100% of the Eddington limit continuously, with zero breaks, starting from the very first moment a black hole could theoretically form. The math still doesn't reach 600 million solar masses by 570 million years after the Big Bang. Scientists have run those calculations many times. The answer keeps coming back the same. With a normal stellar remnant starting point, there simply isn't enough time. Some researchers suggest the black hole could have gone through phases of super Eddington feeding, consuming matter faster than the theoretical ceiling allows. There is some evidence this is physically possible under extreme conditions, but sustaining it long enough to explain this mass requires conditions so rare and specific that invoking it feels like an excuse rather than an explanation. And here's where the mystery deepens further. The 600 million figure is a confirmed minimum. The actual mass could be higher. Webb's measurements give us a baseline, but refining that number requires follow-up observations that are still ongoing. Some estimates push the mass even higher. Every upward revision makes the problem worse. What scientists are left with is an object that either grew from something far more massive than a typical stellar black hole to begin with, or that the early universe contained conditions we've never modeled that allowed for growth rates we've never seen. Both require a fundamental update to how we understand cosmic history. The sheer weight of this black hole isn't just a data point, it's a challenge, a declaration from the early universe that something happened there we haven't figured out yet. And to trace the path toward an answer, we need to go back to the very beginning. Back to what the Big Bang actually left behind and why the environment it created should have made something like this nearly impossible. What came out of that primordial chaos is stranger than most people realize. Most people imagine the Big Bang as an explosion, a flash of light, a burst of energy, and then space filled with stars and galaxies spreading outward in all directions. That picture is almost entirely wrong. The real aftermath of the Big Bang was closer to the inside of a furnace. The entire universe was a dense, screaming hot plasma, a soup of particles and radiation so tightly packed together that light couldn't travel more than a fraction of an inch before being absorbed and re-emitted. There was no clear sky, there were no stars, there was no darkness, because darkness requires an absence of light, and the early universe was saturated with it, just not in any useful form. This state lasted for roughly 380,000 years. Then, something critical happened. The universe cooled just enough for electrons to bond with protons, forming the first neutral hydrogen atoms. The moment that happened, light was suddenly free to travel. The universe became transparent for the first time. That released light is still detectable today, stretched by billions of years of cosmic expansion into the microwave range. Scientists call it the cosmic microwave background, and it's the earliest photograph of the universe we have. Everything before it is physically inaccessible to us. But here's the problem. When the universe became transparent, it also went dark. The plasma glow faded. The first hydrogen atoms settled into vast, cold, structureless clouds. There were no stars yet, no galaxies, no sources of light at all. Astronomers call this era the Cosmic Dark Ages, a period lasting hundreds of millions of years when the universe sat in near total darkness, waiting. During this time, gravity was the only force doing meaningful work. Slowly, painstakingly, it pulled hydrogen and helium gas together into denser and denser clumps. These clumps grew into clouds. The clouds collapsed under their own weight. Eventually, the pressure and heat at the cores of those clouds became intense enough to ignite nuclear fusion. Stars switched on. That transition from dark to light is called reionization. The first stars blasted ultraviolet radiation through the hydrogen fog, ionizing it, clearing the cosmic haze. Gradually, the universe lit up. But here's what matters for our black hole. All of this took time. Real, physical time, governed by how fast gravity can pull scattered matter together. The process of forming even the first primitive stars likely took at least 100 to 200 million years after the universe turned transparent. And those early stars, called population 3 stars, were likely massive and short-lived, burning fast and dying as black holes or neutron stars within a few million years. Even if one of those first stellar deaths produced a black hole immediately, that black hole started small, maybe tens or hundreds of solar masses. From that point, it had roughly 300 to 400 million years, at best, to reach 600 million solar masses before our target object appears in the observational record. That window is brutally short. Picture trying to build a skyscraper in a month, using only hand tools, starting from bare dirt. The materials exist, the physics allows it, but the timeline makes it essentially impossible under normal conditions. Something in the early universe had to break the rules. Something had to give this black hole a head start so dramatic that it could skip entire stages of normal growth. What that something might be is one of the most contested and fascinating debates in modern astrophysics. And it starts with a question almost no one expected to be asking about the early universe. What if a black hole could form without a star at all? After the universe turned transparent, it went silent. The plasma glow faded. The hydrogen fog settled into cold, dark clouds drifting through expanding space. There were no stars burning overhead, no galaxies glowing on the horizon. For hundreds of millions of years, the universe existed in a state of profound, total darkness, lit only by the faint residual warmth of creation itself, slowly bleeding away. Scientists call this era the Cosmic Dark Ages, and it lasted from roughly 380,000 years after the Big Bang until the first stars ignited somewhere between 150 million and 250 million years in. The exact timing is still debated and unconfirmed, but the general picture is widely accepted. During this period, the universe looked almost featureless to any hypothetical observer. Vast sheets of hydrogen and helium gas filled space in near-uniform distribution, interrupted only by the faintest fluctuations in density left over from the Big Bang's initial shock. Those fluctuations were tiny temperature differences of roughly 1 part in 100,000 compared to the surrounding gas. Those tiny differences were everything. Gravity doesn't need much of a head start. Even the smallest density difference means one region has slightly more mass than the regions around it. More mass means more gravitational pull. More pull means surrounding material falls inward. As matter accumulates, gravity strengthens further, pulling in even more. The process is self-reinforcing, slow at first, then accelerating. Over millions of years, those faint ripples in the early universe grew into something tangible. Dense filaments of gas formed along the edges of enormous empty voids. Those filaments intersected at nodes where matter concentrated most heavily. These nodes became the seeds of the first galaxies. But here's the critical piece most people overlook. During the Dark Ages, the gas filling the universe was cold, genuinely cold in astronomical terms. And cold gas behaves differently from hot gas. Cold gas can collapse more easily under gravity because it lacks the internal pressure that hot gas uses to resist compression. This means the Dark Ages may have been the single best window in the universe's entire history for forming extremely massive objects very quickly. The gas was cold, abundant, and for the first time free from the blinding radiation pressure of the plasma era. Gravity had nearly free rein. Some researchers believe that during this narrow window, before the first stars ignited and flooded space with destabilizing ultraviolet radiation, enormous clouds of gas may have collapsed directly and catastrophically, bypassing the usual slow process entirely. If that happened, the result would be objects of extraordinary mass forming in extraordinary timescales. A direct collapse, without stars as middlemen. That window closed the moment the first stars turned on. Their radiation heated and ionized the surrounding hydrogen, destroying the cold, fragile conditions that made rapid collapse possible. Once that radiation spread through space, the shortcut was gone forever. The universe had to grow its structures the slow, hard way from that point forward. This means there may have been a brief cosmic moment, measured in tens of millions of years, when the rules of structure formation were looser than they've ever been since. A moment when something enormous could form without waiting. Whether our ancient black hole was a product of that window is still an open question, theoretically compelling, observationally unproven. But the theory exists for a reason. Because when you look at the math, when you stare at 600 million solar masses sitting in a 570 million year old universe, the Dark Ages collapse model is one of the very few explanations that doesn't immediately fall apart. And the next step in that explanation is even more radical than the darkness itself. The first stars in the universe were monsters. Ancient, massive, burning at temperatures far beyond anything in the modern cosmos. They were nothing like the stars we see today. Scientists call them population 3 stars, and while none have ever been directly observed, theoretical models built from well-tested physics paint a remarkably detailed picture of what they must have been like. They formed from the collapse of pure hydrogen and helium clouds, the only elements the Big Bang produced in meaningful quantities. No carbon, no iron, no oxygen to speak of. Just the two lightest elements in existence, collapsing under gravity and igniting into nuclear fusion at their cores, without heavier elements to help radiate heat away during collapse. These clouds stayed hotter than modern star-forming clouds. Hotter clouds resist fragmentation, meaning instead of splitting into dozens of smaller stars the way modern gas clouds do, early clouds tended to collapse into fewer, far more massive objects. Theoretical models suggest population 3 stars commonly reached masses of several hundred times that of our Sun, with some potentially reaching over 1,000 solar masses. These were not gentle, long-lived stars like the Sun. They burned so hot and so fast that their lifespans measured in millions of years, occasionally less. Compared to our Sun's expected 10 billion-year lifespan, these stars were brief, furious explosions of energy. When they died, the most massive among them collapsed directly into black holes. These stellar remnants were large by modern standards, potentially reaching masses of several hundred solar masses. And scientists originally thought these remnant black holes might be the seeds of the supermassive black holes we see today. Here's the problem: the math still doesn't work. Even starting from a black hole of several hundred solar masses, which is already an optimistic assumption, growing to 600 million solar masses in under 400 million years requires feeding rates at or above the Eddington limit, essentially without interruption. In reality, black hole feeding is messy, chaotic, and frequently interrupted. Radiation from the feeding process itself heats surrounding gas and blows it outward, cutting off the supply. Mergers with other objects send gravitational waves rippling outward, carrying away mass and momentum. The universe doesn't offer clean, uninterrupted buffets. Simulations that start with realistic population 3 stellar remnants and try to grow them to the observed mass within the available time routinely fail. The gap between what the math produces and what observations confirm is too wide to paper over with minor adjustments. Some teams have attempted to salvage the stellar remnant model by proposing unusually high merger rates, chains of black holes combining repeatedly in dense early clusters. These merger scenarios are theoretically possible, but producing enough mergers, fast enough, in a universe that young requires an improbably specific set of conditions stacking up in the same place at the same time. The deeper you push into the stellar remnant model, the more it starts to resemble a house of cards. Each fix requires another fix. Each assumption requires another assumption. Scientists are trained to resist abandoning a working model until the evidence forces them to. The stellar remnant model hasn't been fully abandoned, but the strain is visible. Papers that were confident 5 years ago are now hedged, careful, loaded with qualifiers. And standing behind all of it, quiet and insistent, is the direct collapse theory, waiting for its moment to be taken seriously. What that theory proposes about the early universe challenges something even more fundamental than stellar formation timelines. It challenges whether stars need to exist at all for a black hole to be born. For decades, the story of how supermassive black holes form went something like this. A massive star burns through its nuclear fuel over millions of years. When the fuel runs out, the star's core collapses under gravity in a fraction of a second, triggering a supernova explosion. If the core is massive enough, gravity wins completely, and what remains is a black hole. It starts small, perhaps a few times the mass of the Sun, perhaps a few dozen. From there it grows. Over hundreds of millions, then billions, of years, this black hole pulls in surrounding gas and dust. Material spirals inward through an accretion disk, a flat rotating structure of superheated matter glowing brighter than entire galaxies as it compresses and falls toward the event horizon. Some of that material crosses the horizon and adds to the black hole's mass. Some gets blasted outward in jets of energy. Gradually, patiently, the black hole grows. Galaxies form around these growing black holes. Or perhaps the black holes grow inside, forming galaxies. The relationship is intimate and complicated, and for most of cosmic history, it seemed to work in a rough balance. The bigger the galaxy, the bigger the black hole at its center, scaled by a consistent ratio that held across thousands of systems studied in detail. This model is elegant. It fits the data from most of the universe we can observe. It's backed by decades of observations, computer simulations, and theoretical work from hundreds of researchers across the world, and it completely falls apart when you apply it to the object we're discussing. The issue is a combination of time and speed limits. Accreting mass onto a black hole generates radiation. That radiation pushes back against the infalling gas, slowing the feed rate. The Eddington limit, which you've already encountered, sets the maximum sustainable growth rate for any given black hole mass. To grow by a factor of roughly 1 million, from a few dozen solar masses to hundreds of millions of solar masses, requires an enormous amount of time even at peak efficiency. Scientists have run the numbers from every angle: starting mass, feed rate, merger bonuses, everything included, to reach 600 million solar masses by 570 million years after the Big Bang. A black hole seeded by a population 3 stellar remnant would need to feed at or above the Eddington limit for essentially its entire existence, with almost zero downtime. Astrophysics doesn't offer that kind of consistency. Gas supplies run out. Competing gravitational forces disrupt feeding. The black hole's own radiation blows away the material it needs. In practice, black holes spend significant periods in relative quiet between active feeding phases. Real growth is lumpy, not smooth. Every realistic simulation of early black hole growth from a stellar seed underproduces the observed mass by a wide margin when constrained by the actual age of the universe. The standard model isn't wrong in general. For most of cosmic history, it explains what we see beautifully. The problem is specific and confined to the earliest, most extreme objects. The universe's very first supermassive black holes seem to exist in a regime where the standard rules ran out of runway. What that implies is either a hidden shortcut in the physics, a starting condition we've never accounted for, or a process in the early universe so efficient and so rare that it operated once in a narrow window and never again. The answer, most likely, is hiding in the conditions of the universe before the first stars ever turned on, something waiting in the dark, ready to collapse all at once. Science runs on math. Every theory, every model, every claim about how the universe works has a set of equations behind it. Those equations make predictions. Observations either confirm those predictions or they don't. When they don't, something has to give. The moment researchers locked down the confirmed mass and confirmed age of this ancient black hole and fed both numbers into the standard growth models, the math broke. Loudly, unambiguously, here is the core calculation, stripped of jargon. A black hole growing at the Eddington limit, the absolute physical speed limit for accretion, doubles its mass in a characteristic timescale of roughly 45 million years. That's the E-folding time, the period in which a black hole can grow by a factor of roughly 2.7 under ideal conditions. Starting from a seed of 100 solar masses and doubling repeatedly, you'd need to fit roughly 16 doubling events into the available window just to approach 600 million solar masses. 16 doublings in 500 million years sounds manageable until you remember that each doubling assumes perfect, uninterrupted, maximum rate feeding. No gaps, no blowback, no mergers slowing things down. no competing gravitational forces fragmenting the gas supply. In practice, observed black holes spend significant time in quiet phases where feeding slows to a fraction of the Eddington rate. When researchers plug in realistic duty cycles, the periods when a black hole is actually actively feeding at high rates, the growth falls catastrophically short. Some simulations produce objects a few million solar masses at most within the available window. The observed object is 2 orders of magnitude more massive than that. 2 orders of magnitude is not a rounding error. It's not a small calibration problem. It's a gap so wide that it signals something fundamental is missing from the framework. The calculation became famous within the community. Teams at multiple institutions ran independent versions of it, hoping someone had made an error. Nobody had. The conclusion was reproducible and consistent. Every group that ran the numbers reached the same uncomfortable place. Under standard assumptions, this object cannot exist, and yet, it does. This is the kind of confrontation that reshapes fields. Not a gradual realization that a model needs minor updates, but a hard collision between ironclad math and undeniable observation. When those two things disagree this severely, the resolution never comes from the observation being wrong. The universe doesn't make mistakes. The model does. What the calculation actually shows, stripped of everything else, is that the seed mass had to be far larger than a stellar remnant. The starting point had to be not dozens or hundreds of solar masses, but tens of thousands, possibly hundreds of thousands. Only with a seed that large does the math close within the available time, even at realistic feed rates. That is an extraordinary starting mass. Finding a natural process that creates a black hole seed of 100,000 solar masses in the early universe requires something the standard model doesn't contain. It requires the gas itself to skip the star-forming step entirely and fall directly into a black hole, and the physics for exactly that process, bizarre as it sounds, already exists on paper. The equations allow it. The question is whether the early universe actually triggered it. One group of scientists believes it did. They call the result a direct collapse black hole, and the conditions that made it possible existed for a window so short it may have opened and closed before the first stars in the universe finished forming. What happens inside that collapse is stranger than almost anything else in modern astrophysics. Every black hole you've ever heard of came from something that existed before it. A star that ran out of fuel, a neutron star crushed past its limit, a collision between two dense objects. Black holes, in the standard picture, are endpoints. Things become black holes after living through something else first. The direct collapse theory breaks that chain entirely. Under certain conditions in the early universe, a massive cloud of gas may have skipped the star-forming stage and collapsed directly into a black hole, with no stellar phase in between. The cloud doesn't fragment into a cluster of stars. It doesn't ignite nuclear fusion at its core. It simply falls inward, all at once, under gravity, generating a black hole seed of extraordinary initial mass. The theoretical mass of a direct collapse black hole seed ranges from roughly 10,000 to 100,000 solar masses, depending on the size and conditions of the original gas cloud. Compare that to the few dozen to few hundred solar masses of a typical stellar remnant black hole, and the advantage becomes obvious. A direct collapse seed starts 1,000 to 10,000 times more massive than a stellar seed. Under the same growth rate, it reaches supermassive scales far faster and far more comfortably within the available time window. The math works. Under realistic accretion rates and duty cycles, a direct collapse seed of 100,000 solar masses can plausibly reach 600 million solar masses within 500 million years. The calculation that broke the stellar remnant model holds together with a direct collapse starting point, but the conditions required for direct collapse are extraordinarily specific. And this is where the theory gets both compelling and frustrating. For a gas cloud to collapse directly, rather than fragmenting into stars, it must stay warm enough to resist fragmentation, but cool enough to collapse overall. This sounds contradictory, and in most environments it is. Gas clouds fragment into stars precisely because cooling within the cloud creates cold, dense knots that collapse individually. Preventing fragmentation means preventing that cooling. The main coolant in primordial hydrogen gas clouds is molecular hydrogen, two hydrogen atoms bonded together. Molecular hydrogen radiates energy very efficiently, allowing gas to cool rapidly, which drives fragmentation. For direct collapse to work, the molecular hydrogen must be destroyed before the cloud collapses. The agent that destroys molecular hydrogen is ultraviolet radiation at a specific wavelength range. Intense enough ultraviolet flux bathes a gas cloud, breaks apart the molecular hydrogen, removes the primary cooling mechanism, and leaves the cloud unable to fragment. Instead of spawning stars, the cloud collapses as a single object. The source of that ultraviolet flux? A nearby galaxy already full of young, hot stars. So direct collapse black holes, if they existed, formed in a very specific scenario, a large, cold gas cloud sitting close enough to an active young galaxy to be flooded with ultraviolet radiation, yet far enough away to avoid being torn apart by tidal forces or consumed by that galaxy directly. It's a narrow window, a precise cosmic setup, and it could only have operated in the early universe, before the entire intergalactic medium was ionized by the combined ultraviolet light of countless galaxies, which would have made the conditions both more common and simultaneously more destructive. This is confirmed theory, meaning the physics is mathematically consistent and passes peer review. But it remains an unconfirmed origin model. No direct collapse black hole has ever been caught in the act of forming. The evidence is indirect. For now, because what comes next changes what we can actually see, and just how close we might be to catching one. The early universe offered a set of conditions so specific, so fragile, and so temporary that they may have existed for only a few tens of millions of years before closing forever. If direct collapse black holes are real, they formed inside that window, and once it shut, the universe lost the ability to make them again. Understanding why that window existed requires tracking two competing processes racing against each other in the infant cosmos. On one side, galaxy formation. The first galaxies assembled from collapsing gas clouds, and as their stars ignited, they flooded the surrounding space with ultraviolet radiation. That radiation was necessary to destroy molecular hydrogen and allow direct collapse to occur in nearby gas clouds. On the other side, reionization. As more galaxies formed and more stars turned on, the cumulative ultraviolet radiation from thousands of galaxies began ionizing the hydrogen gas filling the universe. Once hydrogen ionizes, it behaves differently. Ionized gas has its own cooling and heating dynamics that make direct collapse nearly impossible, even with abundant radiation. The window for direct collapse existed in the gap between these two processes. After the first galaxies appeared and started radiating, but before reionization had spread far enough to contaminate the surrounding medium. During that narrow overlap, a cold gas cloud sitting in the radiation zone of a nearby young galaxy could experience the exact right conditions, enough ultraviolet flux to destroy molecular hydrogen, but a surrounding medium still cool and neutral enough to allow overall collapse. Simulations suggest this window lasted somewhere between 10 million and 50 million years. In the lifespan of the universe, that is almost nothing. The placement requirements were also strict. The collapsing cloud needed to sit at a specific distance from its ultraviolet source galaxy. Too close, and tidal forces would shred the cloud, or the radiation would ionize it completely, preventing collapse. Too far, and the ultraviolet flux would be too diluted to destroy molecular hydrogen effectively. allowing fragmentation and star formation to proceed normally. This spatial precision, combined with the narrow time window, means direct collapse black holes would be rare even if the physics allows them perfectly. Cosmological simulations that include these constraints find very few sites across the observable universe where all conditions aligned simultaneously. Some estimates suggest only one direct collapse event per large volume of early universe. Others are more generous. But even the optimistic projections produce a population small enough to explain only a handful of the most extreme early supermassive black holes, exactly the population that baffles astronomers most. There's something almost poignant about this. The universe briefly created the conditions for a faster, more dramatic path to cosmic structure. A shortcut. A cheat code written into the physics of cold hydrogen gas and ultraviolet light. And then, as the universe matured and light spread everywhere, the cheat code expired. Every direct collapse black hole that formed during that window became a seed for something enormous. Billions of years later, some of those seeds sit at the centers of the largest galaxies in existence, having fed and grown across cosmic time into the titans that anchor the large-scale structure of the universe. The one we found at 570 million years old may be one of those original seeds, caught early enough that we can still see the fingerprints of its extraordinary birth. But even this extraordinary origin story raises a deeper question. How do we actually know how old it is? How do we look at a point of light billions of light years away and confidently declare it existed at a specific moment in cosmic history? The answer involves a trick of light so elegant it almost feels like the universe left us a receipt. For most of human history, looking at the early universe was physically impossible. The problem is not ambition or telescope size. The problem is light itself. The most distant objects in the universe are also the oldest, because their light has been traveling toward us for the longest time. The further back you want to see, the older and fainter the light you need to detect. And as that light travels across billions of light years of expanding space, the universe itself stretches it, pulling the wavelengths longer and shifting them toward the red end and then beyond the visible spectrum entirely into infrared. Most of the light from the universe's first few 100 million years reaches Earth in the infrared range. Infrared light carries lower energy than visible light. It's absorbed by water vapor in our atmosphere, and it's overwhelmed by the thermal infrared glow of warm objects, including the telescope itself, if that telescope isn't cooled and positioned carefully. The Hubble Space Telescope, despite its remarkable capabilities, operated primarily in visible and near-infrared wavelengths. It could reach back roughly 13 billion years in cosmic time, but the earliest period of galaxy and black hole formation sat just beyond its grasp, tantalizingly close but technically unreachable. The James Webb Space Telescope changed that. Webb launched in December of 2021 and reached its operating position roughly 1 million miles from Earth, at a gravitational balance point called the second Lagrange point, where it remains shielded from the Sun, Earth, and Moon simultaneously by its enormous sunshield the size of a tennis court. There, passively cooled by the eternal shadow of its own sunshield, its instruments drop to temperatures approaching negative 440 degrees Fahrenheit. At that temperature, Webb's own thermal noise drops low enough to stop contaminating its observations. Webb's primary mirror spans 21 feet across, built from 18 hexagonal gold-coated beryllium segments. Its sensitivity in the near and mid-infrared range exceeds Hubble's by factors of 100 or more in relevant wavelengths. Where Hubble saw dim smudges or nothing at all, Webb resolves structure. The ancient black hole we're discussing was identified in Webb observations designed specifically to hunt for high redshift objects, meaning objects so distant their light has been stretched dramatically by cosmic expansion. The light from this system left its source when the universe was barely 570 million years old, and reached Webb's detectors stretched far beyond what human eyes can see. Webb's instruments captured it in infrared wavelengths corresponding to light originally emitted in ultraviolet, a direct fingerprint of a hot accretion disk around a feeding black hole. This is confirmed observational data, cross-validated by multiple analysis teams. The detection is solid. What Webb revealed was a compact, intensely bright core embedded in a relatively small, faint host galaxy. The brightness of the core, combined with the spectral signatures in the light, pointed unmistakably to a supermassive black hole actively feeding at high rates, generating enormous energy as in falling material compressed and heated in its accretion disk. Without Webb, this object would have remained invisible, a missing piece in the puzzle of the early universe, hiding in infrared frequencies beyond any instrument we had previously built. Webb has now found multiple candidates in this extreme redshift range. Each one raises the same question the math keeps asking. Each one sits in a universe too young to have produced them by conventional means, and the way we date them with such precision is one of the most elegant pieces of physics in modern astronomy. When a police siren drives toward you, the sound waves compress and the pitch rises. When it drives away, the waves stretch and the pitch drops. You've heard this your entire life without necessarily knowing it has a name. Scientists call it the Doppler effect, and it applies to light exactly as it applies to sound. Every source of light moving away from an observer has its light waves stretched. The faster the source moves away, the more the waves stretch, and the more the light shifts toward the red end of the electromagnetic spectrum. Astronomers call this redshift. In our universe, every distant galaxy is moving away from us. The universe is expanding, stretching the space between galaxies constantly. The further a galaxy sits from us, the more space lies between us, and the faster that galaxy appears to be receding as all that intervening space stretches. More recession means more redshift. This creates a cosmic ruler. Measure the redshift of a galaxy's light, and you can calculate how much the universe has expanded since that light left its source. From that expansion factor, you can derive the age of the universe at the moment the light was emitted. Every element in the universe emits and absorbs light at specific, predictable wavelengths, like a fingerprint. Hydrogen always absorbs at the same wavelength. Oxygen always emits at the same wavelength. These patterns are fixed by quantum physics and don't change regardless of where in the universe the atom sits. When astronomers observe a distant galaxy, they look for these known spectral patterns and measure how far they've shifted toward the red end of the spectrum compared to where they should appear. The amount of shift is the redshift value, typically expressed as the letter Z followed by a number. Higher Z means greater distance and earlier cosmic time. The black hole at the center of our story sits at a redshift of approximately 7, meaning the universe has expanded by a factor of roughly 8 since its light left. Translating that expansion factor through our best models of cosmic history places the emission at approximately 570 million years after the Big Bang. This is confirmed with high confidence. The spectral lines that anchor the redshift measurement are clean and unambiguous. Multiple independent teams analyzing the same Webb data have arrived at consistent redshift values. What's remarkable about this technique is its precision. We're not estimating the age of this object by how dim it looks or how small its galaxy appears. We're reading the actual stretch in its light, a direct physical record of how much the universe has expanded since that light began its journey. The universe itself encoded the timestamp. We just learned to read it. One surprising detail: the light we're analyzing left this system over 13 billion years ago. The black hole itself has been evolving this whole time. The object we see in Webb's data is a snapshot of something that has certainly changed dramatically since, possibly merging with other black holes, possibly growing into something far more massive. Sitting now at the center of a galaxy, we might be able to see much closer to us, without realizing the connection. Redshift doesn't just tell us the age of what we're seeing. It reminds us that everything we observe in deep space is ancient history, already transformed into something else by the time we look. And the galaxy this black hole inhabits, small and strained even 13 billion years ago, tells a story of its own that gets stranger the more closely you examine it. Every supermassive black hole at the center of a galaxy is locked in a relationship with its host. They share resources. They influence each other's growth. The black hole feeds on gas that the galaxy provides. The energy the black hole releases regulates how fast new stars can form in the galaxy around it. Over billions of years, this back and forth shapes both objects into what we see today. That relationship assumes a rough balance. A black hole that is large relative to its galaxy pulls hard and feeds heavily, but it also releases enormous energy that pushes gas outward, slowing the galaxy's star formation and eventually cutting off the black hole's own supply. The system self-regulates. That's why we see a consistent ratio between black hole mass and galaxy mass across thousands of systems in the modern universe. The galaxy hosting our ancient black hole doesn't follow this ratio. It violates it dramatically. The host galaxy is estimated to be roughly 1 billion solar masses in total stellar mass. That sounds enormous until you compare it to the black hole at its center, which is at minimum 600 million solar masses. In most galaxies we've ever studied, the central black hole represents roughly a few tenths of a percent of the total galaxy mass. Here, the black hole represents more than half of the stellar mass of the entire galaxy. The black hole is nearly as massive as the rest of the galaxy combined. Picture a human heart so large it fills most of the chest cavity, leaving almost no room for lungs, ribs, or any other organ. The body couldn't function normally. The heart would dominate everything. That is roughly the structural situation this early galaxy faces. A black hole that outsizes its galaxy this severely feeds differently. The gravitational influence of the black hole extends across a larger fraction of the galaxy's total volume, disrupting gas dynamics throughout the entire system. Gas that would normally settle into star-forming regions gets redirected toward the central mass. Star formation rates get distorted. The galaxy's development is warped by its own center. Observations suggest this galaxy already shows signs of that disruption. Its star formation rate appears suppressed relative to what its gas supply should allow, a pattern consistent with the black hole's radiation blowing gas out faster than it can settle and cool. Scientists call this process quenching, and finding it this early in cosmic history, in a galaxy this young, was unexpected. Most quenched galaxies in the modern universe are enormous, ancient systems that burned through their star-forming gas billions of years ago. Finding a tiny, young galaxy already quenched, already being hollowed out by its own central black hole, is a data point that doesn't fit anywhere in the standard picture of galaxy evolution. It suggests that the damage a supermassive black hole does to its host galaxy can happen faster than anyone modeled. That, in extreme cases, the black hole wins the mass competition early, dominates the galaxy's energy budget early, and begins shutting down star formation before the galaxy even reaches maturity. For humanity, this is more than an abstract puzzle. Our own Milky Way hosts a central black hole. It's quieter now, much less active, but understanding what happens when a black hole grows too fast relative to its galaxy tells us something about the history of our own cosmic neighborhood, and possibly about futures we can't yet predict. And the energy driving all of this, the raw output of a feeding black hole, is something almost incomprehensible in scale. Something is about to get very bright. One of the most carefully tested relationships in all of astrophysics is the link between a galaxy's mass and its central black hole's mass. Scientists call it the M-sigma relation, a tight correlation observed across thousands of galaxies spanning a vast range of sizes, ages, and environments. Measure the mass of a galaxy's central bulge of stars. and you can predict the mass of its black hole with impressive accuracy. The ratio holds with remarkable consistency. This consistency is not a coincidence. It reflects real physics. The processes that build galaxies and the processes that feed black holes are intertwined. They share gas supplies. They regulate each other through feedback. The black hole's energy output limits how much gas cools and forms new stars. The galaxy's star formation rate limits how much material flows toward the center. Over billions of years, they settle into a balance that produces the ratio we observe. This relationship became one of the cornerstones of modern cosmology. It allowed scientists to estimate black hole masses from galaxy properties without directly measuring the black holes themselves. It made galaxy evolution models predictable. It felt, for a long time, like a fundamental law. Then, objects like this ancient black hole started appearing. The term astrophysicists now use is overmassive. A black hole is overmassive when its mass significantly exceeds what the M-sigma relation predicts based on its host galaxy's properties. The ancient object we've been tracking is overmassive by a wide margin. Its black hole to galaxy mass ratio sits far above the expected range, outside the scatter of the entire observed population in the modern universe. And it's not alone. Since Webb began delivering data from the early universe, researchers have catalogued multiple high redshift systems where the central black hole appears dramatically overweight relative to its host. This overmassive phenomenon seems to be specifically an early universe pattern. Two explanations are currently competing in the literature, and neither is comfortably settled. The first is that these black holes genuinely formed with extraordinary efficiency through mechanisms like direct collapse, growing faster than their galaxies could keep up. In this picture, the overmassive state is a real physical condition, and the galaxy will eventually grow into a more normal ratio as star formation catches up over billions of years. The second, more unsettling possibility is that our measurements of the host galaxies are incomplete. The galaxies hosting these black holes are faint, compact, and observed at extreme distances. Some researchers argue that Webb is detecting only the brightest central regions of what might be larger, dimmer extended structures we can't fully resolve yet. If the true galaxy masses are larger than current measurements suggest, the M-sigma violation might shrink toward normal. Both views have published support. Neither has decisively won. The truth likely contains elements of both, which is itself a meaningful finding. Our tools are reaching their limits exactly when we need them most precise. What the overmassive problem reveals, at its core, is that galaxy and black hole co-evolution doesn't start in balance. The early universe may have produced black holes that temporarily sprinted ahead of their galaxies, only reaching the stable M-sigma ratio after billions of years of galaxy growth caught up. If that's true, the neat, balanced relationship we observe in the modern universe is the end product of a chaotic, asymmetric beginning, and the engine driving that chaos, the feeding mechanism powering everything, operates on a scale that makes the word violent feel inadequate. When matter falls toward a black hole, it doesn't fall straight in. Anything approaching a black hole carries angular momentum, a spin inherited from the larger motion of the gas cloud or galaxy it came from. Angular momentum is conserved, meaning it can't simply disappear. As material falls inward and the space it orbits shrinks, it must spin faster to conserve that angular momentum. The same way a figure skater accelerates when pulling their arms in. The result is an accretion disk, a flat, rapidly rotating structure of gas and dust spiraling inward toward the event horizon over timescales ranging from thousands to millions of years. The disk is not a calm spiral. It's one of the most energetic environments in the known universe. As material in the disk spirals inward, friction between adjacent layers of gas converts orbital energy into heat. The inner regions of the disk, closest to the black hole, reach temperatures of millions of degrees. At those temperatures, matter radiates light across the entire electromagnetic spectrum, from radio waves through visible light to X-rays, with the inner disk blazing most intensely in extreme ultraviolet and X-ray frequencies. The total power output of an actively feeding supermassive black hole can reach levels that outshine its entire host galaxy by factors of 10 to 1,000. A single point, millions of times smaller than the surrounding galaxy, radiating more energy than every star in that galaxy combined. Scientists call these objects quasars when they're observed at cosmological distances. The word originally stood for quasi-stellar object because early radio telescopes detected point-like sources of energy so bright they were initially mistaken for stars. They are, in reality, the accretion disks of feeding supermassive black holes seen across billions of light-years of space. The ancient black hole we've been tracking was almost certainly a quasar in its early life. Its feeding rate, inferred from the luminosity of its core as seen by Webb, places it firmly in the regime of active, high-rate accretion. The energy it was releasing into its surrounding galaxy during that feeding phase was staggering and consequential. Accretion isn't perfectly efficient. Only about 10% of the mass falling toward the black hole actually crosses the event horizon and gets added to the black hole's mass. The other 90% gets converted into energy and either radiated away as light or launched outward in jets. Those jets, narrow columns of plasma accelerated to near light speed along the black hole's rotation axis, can extend for millions of light years, punching through the surrounding galaxy and into intergalactic space. In the context of our ancient system, a feeding black hole of 600 million solar masses, releasing 10% of its accretion energy as radiation produces an output that would dwarf the entire energy budget of its small host galaxy by a significant margin. That energy heats surrounding gas, pushes it outward, and makes it far harder for the gas to cool, condense, and form stars. This is quenching in real time. The black hole feeds. The feeding generates energy. The energy suppresses star formation. The galaxy around it struggles to grow. What makes the situation at 570 million years after the Big Bang so extreme is that this process was already well underway when the universe was barely 5% of its current age. And it wasn't alone. Across the early universe, other objects were generating similar amounts of light, similar amounts of disruption. The era of the great quasars was just beginning, and it rewrote the history of everything that came after. There was a period in cosmic history when the universe blazed. Between roughly 1 billion and 3 billion years after the Big Bang, an era astronomers call cosmic noon, the universe produced more stars per year than at any time before or since. Galaxies were forming at staggering rates. Gas was abundant, dense, and actively collapsing everywhere. And at the centers of the most massive galaxies, supermassive black holes were feeding at their most intense, their accretion disks pouring out energy that made entire galaxy clusters glow in X-ray light. Those feeding black holes were quasars. And in the era of cosmic noon, they were everywhere. The quasar population of the early universe dwarfs what we see today. The modern universe is relatively quiet. Most supermassive black holes, including the one at our galaxy's center, sit in a low-activity state. Their accretion rates a fraction of what they were billions of years ago. The gas supplies that once fed them richly have been depleted, blown out, or locked up in stars. We see only occasional active galactic nuclei where gas is still falling in at meaningful rates. Go back far enough, and the picture reverses completely. High redshift surveys with Webb and earlier telescopes reveal that in the first few billion years of cosmic history, actively feeding black holes were common. The quasar space density, meaning how many exist per unit volume of the universe, peaks sharply at cosmic noon and drops by orders of magnitude between then and now. Our ancient black hole, sitting at 570 million years old, predates even cosmic noon. It was active before the universe hit its peak star formation rate. It was feeding during the very earliest phase of large-scale structure assembly. This matters because quasars are the most powerful persistent energy sources in the universe, and their energy does work on scales that shape the entire history of galaxy formation around them. A single quasar can deposit more energy into its surrounding intergalactic medium in 1,000,000 years than the combined light of its host galaxy over its entire lifetime. That energy heats gas. Hot gas doesn't collapse into galaxies easily. It floats in diffuse halos around galaxy clusters, too warm to sink to the center and cool. This means an active quasar in the early universe wasn't just affecting its own galaxy. It was heating gas that would otherwise have flowed into dozens of surrounding galaxies, suppressing structure formation across a region millions of light-years wide. A single active black hole, influencing the formation of galaxies it will never directly touch. If the ancient object we've been tracking was in a high-activity quasar phase during its early life, and the evidence from Webb suggests it was, then it was participating in this broader reshaping of cosmic structure from an extraordinarily early date. It was altering the environment around it before most of the universe had even decided what shape it wanted to take. But there's a competing theory for how this black hole grew so massive so fast that doesn't invoke the solitary collapse of a single gas cloud. It involves a chain of events, multiple black holes, and a question about whether mergers could have accomplished what single object growth could not. The answer, it turns out, depends on a problem that has nothing to do with black holes and everything to do with time. Gravity is the universe's great assembler. Over time, it pulls objects together, combines them, builds larger structures from smaller ones. Galaxies merge, star clusters merge, and black holes, inevitably, merge too. When two galaxies collide, their central black holes don't immediately fall together. The black holes sink toward the new combined galaxy's center through a process called dynamical friction, gradually losing energy to the surrounding stars and gas. This in-spiral can take hundreds of millions to billions of years depending on the masses involved and the density of the surrounding environment. Eventually, if the in-spiral completes, the two black holes reach separations so small that gravitational wave emission takes over, radiating away the remaining orbital energy and driving the final plunge. The merger is catastrophic and fast, releasing a burst of gravitational waves and producing a single, more massive remnant. Scientists have directly detected gravitational waves from black hole mergers using detectors like LIGO, confirming that this process is real and measurable. Those mergers involved stellar mass black holes. Supermassive black hole mergers, while theoretically certain to occur, haven't been directly observed yet. But the physics is well established. The merger theory as an explanation for extreme early mass runs as follows. Instead of a single black hole growing continuously, perhaps a population of moderately massive black holes assembled in the dense early universe, fell together through a series of mergers and built up to 600 million solar masses through accumulation rather than feeding. It's an appealing idea. Mergers add mass in chunks rather than waiting for slow accretion. Dense early environments with lots of gas and compact structure formation could plausibly drive multiple merger events in a short time. The problem is the timeline, and it's severe. For a merger chain to explain this object's mass, you need multiple supermassive or near-supermassive black holes to exist in the same region by roughly 500 million years after the Big Bang. But where did those black holes come from? They face the same origin problem as the one we've been investigating. You've only pushed the question back one level. Furthermore, the in-spiral timescale for two massive black holes orbiting in a galaxy-sized environment is long. Models consistently find that bringing two black holes from initial post-galaxy merger separations down to gravitational wave emission ranges requires hundreds of millions of years, at minimum, often longer. In a universe only 570 million years old, there simply isn't room to complete enough mergers to add meaningful mass. Some models propose wet mergers, where the gas-rich early universe provides the extra dynamical friction needed to dramatically accelerate the inspiral. Gas-rich mergers may indeed operate faster than gas-poor ones. But even optimistic wet merger timescales struggle to compress multiple major mergers into the available window without invoking conditions so extreme they effectively require a direct collapse-level head start anyway. The honest assessment from the research community is that mergers almost certainly played a role in building this object's mass over time, but cannot explain its mass by the date we observe it without a large initial seed already in place. The merger theory and the direct collapse theory are likely partners, not competitors. Direct collapse provides the massive seed. Subsequent mergers and accretion build on top of it. But what if there's an entirely separate scaffold helping everything assemble faster? Something invisible, something that makes up most of the universe's mass yet has never been directly detected. Something that may have been the silent architect of the entire early cosmos. Most of the universe's mass is invisible. That statement is not a theoretical speculation. It's a well-confirmed observational conclusion supported by decades of independent evidence from galaxy rotation curves, gravitational lensing, cosmic microwave background analysis, and large-scale structure surveys. Ordinary matter, everything made of protons, neutrons, and electrons, accounts for roughly 5% of the universe's total mass energy. The remaining 27% of matter is something scientists call dark matter, a substance that interacts gravitationally but produces no detectable electromagnetic radiation. It doesn't emit light, absorb light, or reflect light. It simply gravitates. Dark matter's existence was first strongly inferred from the observation that galaxies rotate in ways ordinary matter alone cannot explain. Stars in the outer arms of galaxies orbit at speeds that would sling them free into intergalactic space, if only the visible mass of the galaxy were holding them. Something extra, distributed in a large invisible halo around every galaxy, provides the missing gravitational grip. But dark matter's role in the early universe may be even more fundamental than stabilizing mature galaxies. In the standard cosmological model, dark matter was the first substance to begin clumping after the Big Bang. Ordinary matter, in its plasma state, was tightly coupled to radiation pressure during the early universe, prevented from clumping by the fierce light field permeating everything. Dark matter, immune to radiation pressure, was free to begin gravitational collapse immediately. As dark matter clumped into halos, it created gravitational wells, regions of enhanced gravity into which ordinary matter later fell once conditions allowed. When the universe became transparent and ordinary matter decoupled from radiation, it fell preferentially into these pre-existing dark matter halos, assembling galaxies and black hole seeds in locations that dark matter had already prepared. This means dark matter effectively preceded the structure of the universe before ordinary matter could act on its own. It drew the blueprint. Ordinary matter filled it in. For the formation of early supermassive black holes, this scaffolding could be crucial. A dark matter halo of sufficient mass concentrates ordinary gas more efficiently and more rapidly than gravity from ordinary matter alone could achieve. The deeper the gravitational well, the faster gas falls in, the denser the resulting concentration, and the more favorable the conditions for rapid black hole growth or even direct collapse. Some theoretical models specifically propose that the most massive dark matter halos in the early universe, the rare statistical peaks in the dark matter distribution, hosted the conditions necessary for direct collapse black hole formation. The ultraviolet flux required to destroy molecular hydrogen, combined with the deep gravitational well of a massive dark matter halo. may have created the precise environment where a gas cloud could collapse directly without fragmenting. In this picture, our ancient black hole didn't form randomly. It formed at the site of one of the densest, most massive dark matter concentrations in the early universe, a peak that was practically destined to host something extreme. The dark matter we can't see may have written the address of every supermassive black hole in the universe before the first star ever turned on. Whether that's the full explanation or just part of one remains an open and actively debated question. The observational evidence for dark matter's role in early black hole formation is indirect, filtered through simulations that match observations but can't be directly confirmed with current technology. And the fact that multiple ancient extreme black holes are now being found at similar redshifts in Webb's data suggests this wasn't a single freak occurrence. There may be a population of these objects, each one sitting at the site of an ancient dark matter peak, each one a monument to a universe that built its largest structures before it had finished deciding what rules to follow. And each new discovery pulls the timeline back a little further toward the Big Bang, raising a question that gets more alarming with every answer we find. This object was not the first to break the rules. It was the latest in a growing list. Before Webb began delivering data, the confirmed population of supermassive black holes in the very early universe was small. Ground-based telescopes and Hubble had identified a handful of high redshift quasars, objects sitting at cosmic distances corresponding to the universe's first billion years. Each one was surprising. Each one pushed theorists to revise their models slightly, tighten their assumptions, find ways to make the existing framework accommodate the outlier. Then Webb turned on, and the outliers started multiplying. Within its first 2 years of operation, Webb identified multiple black holes at redshifts corresponding to the universe's first few 100 million years, a period previously almost entirely inaccessible to observation. Some of these systems are confirmed with high confidence. Others are strong candidates awaiting follow-up spectroscopy. Together, they form a picture that is fundamentally harder to dismiss than any single discovery could be. One system detected by Webb sits at a redshift, placing it approximately 400 million years after the Big Bang, over 100 million years earlier than the object we've been examining. Its black hole mass is still being refined, but preliminary estimates suggest it falls in a range that poses the same fundamental growth rate problem, scaled to an even more compressed timeline. Another cluster of early detections reveals what appears to be a population of moderately massive black holes at redshifts between 6 and 10, corresponding to the universe's first 500 million to 900 million years. These objects aren't individually as extreme as the most massive examples, but their sheer number challenges models of early black hole formation. There are more of them than standard theory predicted. Each new discovery functions like an additional data point pressing against the standard model from the same direction. One anomaly can be a measurement error or a rare statistical fluke. 2 anomalies suggest the error bars need widening. A dozen anomalies in the same direction signal a systematic problem with the underlying model. The community crossed that threshold. Researchers who spent years defending incremental updates to the standard framework have begun publishing papers that acknowledge a more fundamental revision may be necessary. The language in journal abstracts has shifted noticeably, from challenges our models to requires new physics in the span of a few years. What makes this progression alarming rather than merely interesting is the directionality. Every new record-breaking early black hole makes the problem harder. The previous record holders were already difficult to explain. Their successors are more difficult. The trajectory of discoveries is moving consistently toward earlier formation times and higher masses, exactly the direction that compresses the available growth window and makes standard models less viable. At some point, if the trend continues, the observations will require a starting condition so massive and so early that it essentially demands direct collapse. or something even more exotic as the only viable explanation. Scientists are careful with that kind of language. Extraordinary claims require extraordinary evidence, but the weight of accumulating extraordinary evidence is exactly what forces extraordinary conclusions over time. The current situation in early black hole research feels less like a single mystery and more like a systematic unraveling. Thread by thread, each Webb detection pulls at the same part of the fabric. And behind every confirmed detection lies a deeper concern. For every object Webb can see, there may be many it cannot. Objects too faint, too obscured by dust, too far into infrared wavelengths even for Webb's extraordinary sensitivity. The confirmed population may be only the visible tip of a much larger early black hole census. If the hidden population is substantial, the formation problem doesn't just get harder, it gets catastrophic for the standard model. What lies just beyond Webb's sight, and what finding it would mean, is one of the most pressing questions in modern astronomy. For most of modern astronomy's history, the answer felt obvious. Galaxies formed first. Black holes grew inside them, fed by the gas and stellar debris those galaxies provided. The galaxy was the house. The black hole was a tenant that grew large over time. That story made intuitive sense. Galaxies are enormous structures, assembled from billions of solar masses of gas collapsing across millions of light years. Black holes, whatever their final size, start small. The galaxy provides the raw material, the black hole consumes it. But a growing body of evidence from the early universe suggests the relationship may have operated in reverse, at least in extreme cases. Some of the most massive early black holes appear to predate their host galaxies in any meaningful structural sense, or to have grown so fast that they dominated the galaxy's evolution from the very beginning, rather than being shaped by it. If a black hole forms through direct collapse before a proper galaxy has assembled around it, what you have is a massive gravitational anchor sitting in a diffuse cloud of gas. That black hole's gravity begins pulling in surrounding material, organizing it, concentrating it. The intense radiation from its accretion disk heats and churns the local gas, driving outflows that push material into filaments and shells. The black hole's jets punch into the surrounding medium, compressing gas along their edges and potentially triggering star formation in regions they wouldn't otherwise have reached. In this scenario, the black hole isn't a byproduct of galaxy formation, it's a catalyst for it. The early galaxy assembles around the black hole's gravitational and energetic influence, shaped by it from the start. This idea, sometimes called the black hole first model, has gained significant theoretical traction in recent years. Simulations that include massive early black holes producing strong radiation and jet feedback produce galaxy morphologies and star formation histories that better match some of the extreme early systems Webb is finding than simulations that grow black holes inside preformed galaxies do. Observational evidence is accumulating cautiously. The overmassive black holes in early galaxies hint that in some cases, the black hole genuinely was the dominant component first. The suppressed star formation in the host galaxy of our ancient 570 million year object suggests the black hole was already controlling the galaxy's development at an epoch when the galaxy should have been in its most active growth phase. The stakes of getting this relationship right extend far beyond abstract cosmology. If black holes seeded and shaped early galaxies, then every galaxy in the universe today, including our own Milky Way, bears the imprint of a black hole that may have been there before the galaxy's first stars. The structure of every spiral arm, the distribution of every stellar population. The chemical enrichment history of every galaxy may reflect the early influence of a central black hole that organized the raw material before the galaxy recognized itself as a galaxy. Our own cosmic home may have been assembled around an ancient gravitational engine rather than growing organically and then acquiring one. That possibility fundamentally changes the story of where we came from. The sun, the earth, the molecules in your body may all trace their origin not to an independently forming galaxy, but to the chaotic environment organized by a black hole that existed before the Milky Way had a name. The energy that made all of that possible is staggering, and understanding how a feeding black hole can simultaneously destroy its surroundings and create the conditions for new structure requires understanding a process so extreme it reshapes everything it touches. A black hole feeding at its maximum rate is, in a specific and measurable sense, destroying itself. The energy released by an actively accreting supermassive black hole doesn't vanish quietly. It interacts with everything around it. Radiation pressure pushes on gas. Jets drill through the surrounding interstellar medium. Winds driven by the accretion disk's own radiation sweep outward at thousands of miles per second, catching gas clouds and accelerating them to escape velocity. The galaxy becomes a machine that converts infalling gas into outflowing energy, and eventually that energy overwhelms the supply. Scientists call this process AN feedback, where AN stands for active galactic nucleus, the formal term for an actively feeding supermassive black hole. The feedback is real, measurable, and consequential. In the modern universe, ANGNI feedback is thought to be primarily responsible for why the largest elliptical galaxies stopped forming stars billions of years ago. Their central black holes grew massive, fed intensely, and their feedback energy heated and expelled the galaxy's gas reservoir so thoroughly that star formation essentially ceased. For our ancient system at 570 million years after the Big Bang, this process appears to have already been operating. The host galaxy shows suppressed star formation relative to what its available gas should allow. Something has been heating or expelling its gas supply. Given the mass of the central black hole and the inferred accretion rate from Webb's luminosity measurements, the black hole's energy output is the obvious culprit. The troubling aspect is how early this is happening. Galaxy quenching in the modern universe is a process that typically takes billions of years to complete, with the black hole cycling through active and quiet phases while gradually depleting the galaxy's gas. In this system, the quenching appears to be underway at an age when the galaxy should be nowhere near finished growing. An analogy helps here. Imagine a forest fire that starts at the moment a forest finishes sprouting its first saplings. The forest never gets to grow. The fire consumes it before it matures. That is effectively what this black hole may be doing to its host galaxy, burning through the raw material of stellar growth before the galaxy can use it to build itself up. For nearby galaxies that interact with this system, the consequences extend further. The outflows from an intensely feeding quasar carry energy far beyond the host galaxy's boundaries, heating the surrounding intergalactic medium over a region potentially millions of light years across. Gas that might have eventually fallen into neighboring galaxies and formed stars instead gets heated and pushed outward, suppressing structure formation across a wide volume. One supermassive black hole in the early universe, feeding hard, can alter the development of its entire cosmic neighborhood. Scaling this up, if dozens or hundreds of such objects existed in the early universe simultaneously, which Webb's observations suggest is plausible, their collective feedback energy may have shaped the large-scale structure of the cosmos in ways we're only beginning to quantify. The distribution of galaxies, the size of cosmic voids, the clustering of galaxy groups may all carry the fingerprints of these early, violent feeders. The early universe wasn't just a place where things were assembling. In some regions, it was a place where things were already being torn apart and rebuilt by the energy outputs of objects that formed too fast and burned too bright. And the question of whether any of those violent early feeders left behind something detectable, something we could find today if we looked in the right place, leads to an answer that changes what we think we know about our own cosmic backyard. A single star produces light. Billions of stars in a galaxy produce more light. But a supermassive black hole feeding at its peak outshines every star in its galaxy combined, sometimes by a factor of 1,000. That comparison doesn't fully convey the consequence. It's one thing to say a source is bright. It's another to understand what that brightness does to the environment around it. The radiation from an accreting supermassive black hole spans the entire electromagnetic spectrum, radio waves from relativistic jets stretching millions of light-years, infrared from the outer accretion disk, visible and ultraviolet light from the hotter inner regions, X-rays from the innermost disk and corona, a hot diffuse region of plasma sitting above the disk, gamma rays in the most extreme cases. Each type of radiation interacts differently with the surrounding gas and dust. Ultraviolet photons ionize hydrogen atoms, stripping away electrons and converting neutral gas into a plasma. X-rays penetrate deeper into gas clouds, heating their interiors directly. The combined radiation field from an active quasar can ionize and heat gas across tens of thousands of light-years in every direction. For a galaxy trying to form stars, this is catastrophic. Star formation requires cold, dense molecular gas clouds. Cold gas collapses. Dense gas collapses faster. But if radiation from the central black hole heats the surrounding medium above a critical temperature, the gas pressure rises enough to prevent collapse. The clouds that would have become stars become diffuse warm gas instead, dispersed rather than concentrated. This is one of the primary mechanisms by which Ang feedback quenches star formation. The radiation field alone, without jets or winds, can suppress an entire galaxy's star-forming activity if the central black hole is massive enough and active enough. In the context of the early universe, this radiation had an additional effect on the broader cosmic scale. The era when the most massive early quasars were most active coincided with the period of cosmic reionization, when the universe transitioned from a neutral hydrogen fog to a fully ionized transparent medium. For years, astronomers debated what provided most of the ionizing photons that drove reionization. Massive young stars were the primary candidates, but high-luminosity quasars, even rare ones, produce enormous numbers of ionizing photons per object. Recent research suggests that early quasars contributed meaningfully to reionization, possibly more than previously credited. Some models now suggest that the most luminous early quasars each ionized enormous bubbles in the surrounding neutral hydrogen, and that these ionized bubbles eventually merged as more quasars and galaxies turned on, completing the transition to a fully transparent universe. Our ancient black hole, feeding intensely at 570 million years after the Big Bang, would have been doing exactly this, carving out an enormous ionized region around itself, clearing the cosmic fog locally before the fog cleared globally. It was reshaping the universe's transparency while simultaneously dismantling its own host galaxy's ability to grow. Two transformations at once, one on the scale of a galaxy, one on the scale of the observable universe. And the question that follows naturally is whether something like this could happen again, whether the conditions that produced this object might recur, whether somewhere in the universe today or in the distant future, a black hole might form and feed with similar ferocity. The answer requires understanding something that almost no telescope can see, an edge built into the observable universe itself. Webb is the most powerful space telescope ever built. Its infrared sensitivity, its mirror size, its stable operating position far from Earth's thermal noise, all of it combines into an instrument that can detect individual galaxies from the universe's first few 100 million years. It has already transformed our picture of the early cosmos in just a few years of operation. And it still has limits. The most fundamental limit is sensitivity. Every telescope, no matter how advanced, can only detect objects above a certain brightness threshold. Below that threshold, objects exist in the data as noise, indistinguishable from detector fluctuations and background radiation. In the early universe, many objects are intrinsically faint, small galaxies hosting moderately massive black holes that never reached quasar luminosities. These objects may constitute the majority of the early black hole population, yet they sit below Webb's detection floor. A second limit is wavelength coverage. At the highest redshifts, the diagnostic spectral lines astronomers use to confirm distances and measure black hole masses shift into mid-infrared wavelengths. Webb's mid-infrared instrument can reach there, but its sensitivity in those ranges is lower, and observations require significantly longer exposure times. Complete spectroscopic surveys of the highest redshift candidates are slow and expensive in telescope time. A third limit is obscuration. Many actively feeding black holes in the early universe were surrounded by dense clouds of gas and dust produced by the intense star formation occurring in their host galaxies. Dust absorbs shorter wavelength light and re-emits it at longer wavelengths, making the black hole core nearly invisible at optical and near-infrared wavelengths. Some of the earliest, most massive black holes may be completely buried behind dust screens that even Webb's near-infrared channels can't penetrate. These dusty, obscured black holes represent a potentially enormous hidden population. Studies of quasar demographics in the modern universe find that a significant fraction of actively feeding black holes at any cosmic epoch are dust-obscured. If the same fraction holds in the early universe, or if obscuration is even more common due to the dense, chaotic conditions of early galaxy formation, then Webb's confirmed detections represent only the optically accessible portion of a much larger population. Some estimates suggest that for every clearly detected early supermassive black hole, several more may exist behind dust barriers in the same redshift range, invisible to current observations. If the hidden population is proportionally similar to the detected one in terms of masses and growth histories, the total number of extreme early black holes becomes dramatically larger. That larger number puts even more pressure on formation models. Direct collapse events need to be less rare than current estimates suggest, or some other mechanism equally capable of producing massive seeds needs to be operating more widely. The next generation of observatories, particularly space-based mid-infrared and submillimeter telescopes, are designed specifically to pierce through dust and reach the hidden population. Ground-based, extremely large telescopes under construction will provide the spectroscopic follow-up speed needed to confirm candidates at scale. The confirmed discoveries are already extraordinary. What the hidden population reveals once we can see it may be more extraordinary still. And there is an even harder boundary beyond observational limits. A wall built into the structure of the universe itself that no telescope, no matter how advanced, will ever fully cross. Every telescope looks back in time. Light travels at a fixed speed, roughly 186,000 miles per second, and the universe is vast. The light arriving at Webb today, from the most distant detected galaxies, left its source over 13 billion years ago. We are seeing those galaxies as they existed when the universe was a fraction of its current age. Push further, and you hit a fundamental limit that has nothing to do with technology. The universe is approximately 13.8 billion years old. Light has been traveling since the Big Bang. The most distant light that could possibly have reached us by now left its source at the moment of the Big Bang itself, roughly 13.8 billion years ago. That defines the observable universe, a sphere centered on Earth with a radius of roughly 46 billion light-years. The radius is larger than the age in light-years because the universe has been expanding the whole time the light was traveling. Beyond that sphere, light from objects there simply hasn't had time to reach us. Those objects exist. Physics requires them to. The universe almost certainly extends far beyond the observable bubble, possibly infinitely. But the light from those regions is still in transit. It will never reach us in any meaningful time frame, because the universe's expansion is carrying those regions away faster than light from them can close the gap. This is the cosmic horizon, and it is absolute. No instrument improvement breaks it. No engineering solution circumvents it. It's a fundamental consequence of the speed of light and the age and expansion rate of the universe. Within the observable universe, there is a further practical limit on the oldest light we can detect. The cosmic microwave background represents the light released when the universe became transparent, roughly 380,000 years after the Big Bang. Before that moment, the universe was opaque plasma. Light couldn't travel freely. Any light generated before that era was absorbed and re-emitted constantly, losing all information about its original source. We can detect no photons from before recombination, regardless of telescope capability. This means there is a hard observational barrier at approximately 380,000 years after the Big Bang. Everything before that moment is physically sealed behind the plasma fog. For the study of early black holes, the practical frontier lies between the cosmic microwave background and the earliest objects Webb can detect. Somewhere in that gap, the first stars formed, the first black holes appeared, and the conditions for direct collapse either occurred or didn't. We can infer what happened there from the objects we find on our side of the barrier, but we can never directly observe the event itself. This is a deeply strange scientific situation. We have overwhelming evidence that something extraordinary happened in the universe's first few 100 million years. We have confirmed detections of its consequences, but the event itself, the actual formation of the first supermassive black holes, occurred inside an observational shadow we can only approach asymptotically. Every new detection at higher redshift is a step closer to that shadow. Every step reveals more of the picture. But the final answer, the direct observation of a direct collapse black hole forming in real time, may lie permanently beyond reach. We are archaeologists reading the story of a fire from the shape of the ash, knowing we will never see the flame. Cosmology has a timeline, a carefully constructed, extensively tested, broadly agreed upon sequence of events describing how the universe evolved from the Big Bang to the present. It is one of science's great achievements, a framework built from decades of observations and theoretical work that correctly predicts an enormous range of phenomena. The discovery of this black hole and the accumulating population of early cosmic objects Webb is revealing requires revising that timeline in specific and significant ways. The standard timeline placed the formation of the first supermassive black holes late in the first billion years, after sufficient time had elapsed for stellar remnant seeds to grow through accretion. It placed large-scale galaxy quenching, the shutdown of star formation by Ang feedback, as a phenomenon primarily of the universe's second and third billion years, after the largest galaxies had already assembled most of their stellar mass. Both placements are now demonstrably wrong, at least for the most extreme early systems. Confirmed supermassive black holes exist at 570 million years and below. Galaxy quenching driven by Ang feedback is confirmed operating at similar epochs in at least some systems. The timeline must move, and the required revision is substantial enough that it's forcing a reconsideration of the entire sequence of early cosmic events. The revision isn't just a number change, it's a change in mechanism. Moving the formation date of these black holes earlier requires a faster, more efficient formation process than the standard model contains. It requires either direct collapse or super Eddington accretion sustained over longer periods than models typically allow, or some combination of exotic seed masses and unusually favorable environments. All of these options require adding new physics or new conditions to the standard framework. What exactly gets revised is still actively debated. The Lambda CDM model, the standard cosmological model describing a universe with cold dark matter and a cosmological constant driving accelerated expansion, remains the best overall framework we have. Its large-scale predictions are confirmed with extraordinary precision. Galaxy clustering, the acoustic peaks in the cosmic microwave background, the expansion history of the universe, all match the model's predictions beautifully. The problem is specifically in the details of how the first massive objects formed. The Lambda CDM model doesn't specify a unique mechanism for this. It provides the gravitational scaffolding but leaves the baryonic physics, how gas actually forms stars and black holes, to sub-models that have more freedom and more uncertainty. The revisions happening now are primarily to these sub-models. The cosmological skeleton stays intact. The story of what assembled itself onto that skeleton in the first billion years is being rewritten. What that rewriting implies about processes we've never directly observed, about a cosmic era that left only indirect fingerprints, opens a set of questions that cut to the heart of how structure forms in the universe. And some of those questions reach directly back to our own origin. Between the Big Bang and the first confirmed objects Webb can detect lies a gap. An era of cosmic history covering the first 100 to 200 million years after the universe became transparent, during which the first structures assembled in complete darkness, and during which whatever seeded the most extreme early black holes either occurred or failed to occur. Scientists call this the cosmic dawn, the period just before and during the ignition of the very first stars. It is the least observationally constrained period in cosmic history, the chapter we know the most about theoretically and the least about empirically. What happened during cosmic dawn, according to current best models, followed a sequence shaped by dark matter halos drawing in baryonic gas, cooling and condensing that gas into the first molecular clouds, and eventually producing the first population 3 stars in regions of highest density. The timescales involved range from tens to hundreds of millions of years, but the models carry significant uncertainty. The properties of population 3 stars, their mass distribution, their lifetimes, their feedback effects on surrounding gas, are all inferred from theoretical reasoning rather than direct observation. No population 3 star has ever been detected individually. Their expected brightness, combined with their great distance, places them below current detection limits. Webb may eventually detect the collective light of early population 3 stellar populations statistically, but individual detections remain out of reach. Into this uncertain picture, the direct collapse scenario inserts its critical event. At some point during cosmic dawn, in a small number of locations where conditions aligned exactly right, a gas cloud may have bypassed the population 3 stellar phase entirely and collapsed directly. The window for this was narrow, the conditions were specific, and the result was a black hole seed of enormous initial mass sitting in a universe that was still otherwise building its first primitive stars. If direct collapse happened, its products would be among the very first massive objects in the universe. They would predate most galaxies. They would predate most stars. They would sit at the absolute frontier of cosmic structure formation, predating even the objects we can barely detect with Webb. The most extreme possibility in the current literature is that some direct collapse events occurred so early, within the first 100 million years after recombination, that their products sit at redshifts entirely beyond Webb's confirmed detection range. We infer their existence from the extreme masses of objects we do detect. Running the growth calculation backward in time, every confirmed early supermassive black hole is, in this sense, a message from an even earlier era. The message reads, "Something was here before me. Something gave me my head start. Find it if you can. We have not yet found it. We may be close." 4 million solar masses. That's the confirmed mass of Sagittarius A star, the supermassive black hole sitting at the center of our Milky Way, roughly 26,000 light-years from Earth. Compared to the 600 million solar mass object we've been investigating, it seems almost modest. 150 times less massive. A quiet, mostly dormant gravitational anchor in a mature galaxy, currently pulling in only trace amounts of material and producing almost no detectable radiation. But Sagittarius A star has a history, billions of years of feeding, merging, and growing that left it at 4 million solar masses today. And that history raises a question with direct personal stakes. Did our galaxy's central black hole begin its existence through the same extraordinary process that produced the ancient giant we found in the early universe? There is no direct way to observe what Sagittarius A star was doing 13 billion years ago. Its current state tells us nothing about its formation mechanism. 4 million solar masses is consistent with either a stellar remnant seed that grew slowly, or a smaller direct collapse seed that grew at moderate rates, or a direct collapse seed of similar initial mass that grew to its current size efficiently. The endpoint doesn't uniquely identify the path. What we do know is that the Milky Way formed in a massive dark matter halo, one of the larger concentrations in our region of the universe. The galaxy's structure, the distribution of its oldest stellar populations, the chemical composition of stars in its central bulge, all reflect a formation history in an environment of elevated density and active early assembly. Simulations of Milky Way mass halos in the Lambda CDM model consistently produce central black holes that grow rapidly in the first billion years, slower thereafter. Some of those simulations find that a direct collapse event in the host halo during cosmic dawn is the most natural explanation for the early mass budget of the central black hole. Whether that's what actually happened for the Milky Way is unknown. Confirmed, it is not. But the circumstantial case is present and taken seriously in the literature. If Sagittarius A star did originate from a direct collapse event, then the black hole at the center of our galaxy is older than most of the Milky Way's stars. It would have existed, feeding and growing, before the disk of our galaxy assembled, before the spiral arms formed, before the sun condensed from a molecular cloud 4.5 billion years ago. The sun formed inside a galaxy already organized around an ancient black hole that may have been there for 9 billion years before the first photon from our star ever shone. That reframing of our galaxy's origin changes the hierarchy. The black hole didn't arrive late into a formed galaxy. The galaxy assembled around it. The sun, the earth, the chemical elements that make up every living thing on this planet were processed through stars that formed in a galaxy whose structure was set by a gravitational anchor of possibly extraordinary origin. Our entire cosmic home may be the echo of a direct collapse event that happened when the universe was barely 100 million years old. 4 million solar masses versus 600 million solar masses. The ratio sounds abstract until you translate it into something physical. Sagittarius A star, the black hole at the center of the Milky Way, has an event horizon roughly 15 million miles across. That sounds enormous, but in astronomical terms, it fits comfortably within the orbit of Mercury around the Sun. It is gravitationally powerful at close range, but its direct influence on stars and gas is felt most intensely only within a few light-years of the galactic center. The ancient black hole from 570 million years after the Big Bang, at 600 million solar masses, has an event horizon roughly 2 billion miles across. That's large enough to swallow the orbit of Saturn, drop it into our solar system, and every planet out to Saturn would sit inside its event horizon. The Sun itself would be well within its gravitational boundary. The tidal forces at the event horizon of a black hole this size are counterintuitively weaker than those at Sagittarius A star's event horizon. With a supermassive black hole, The event horizon is so large that the difference in gravitational pull between your head and your feet, crossing it, would be relatively gentle. You'd cross the point of no return without immediately feeling anything unusual. The destruction would come later, as you fell deeper and space-time curvature became catastrophic. From a distance, the gravitational influence of a 600 million solar mass black hole dominates the dynamics of its host galaxy across a far larger volume than Sagittarius A star influences the Milky Way. The radius within which a black hole's gravity dominates over the galaxy's own gravitational potential scales with black hole mass. For Sagittarius A star, this radius, called the sphere of influence, extends a few light years. For a 600 million solar mass object, the sphere of influence extends hundreds of light years, encompassing a significant fraction of the host galaxy's inner structure. Inside that sphere, every gas cloud, every forming star, every orbiting stellar remnant feels the black hole more strongly than it feels the galaxy. Gas dynamics, star formation, chemical enrichment, all are regulated by proximity to the central mass rather than by the galaxy's broader potential. For the small host galaxy of our ancient black hole, with its total stellar mass of roughly 1 billion solar masses, having a central object with a sphere of influence this large means the black hole effectively controls the dynamics of a disproportionate fraction of the entire galaxy. A galaxy where the central black hole's gravity reaches far enough to touch the orbits of a meaningful fraction of all its stars is a profoundly different environment from the Milky Way, where Sagittarius A star's influence is confined to a small, dense central region. The difference in scale between these two objects represents not just different masses, but different relationships between a black hole and the universe it inhabits. And the gap in our understanding of how the universe produces objects at both ends of that scale is exactly what the next generation of instruments is being built to close. Every theory of early supermassive black hole formation ultimately depends on a seed, a starting mass, a black hole that existed before the growth really began. Find the seed, confirm its mass, trace its origin, and the entire mystery of how 600 million solar masses assembled in 570 million years becomes solvable. The seed has never been found. This is not for lack of looking. Theorists have proposed 3 main seed categories, each with a different mass range and a different formation mechanism. Light seeds, formed from population 3 stellar remnants, typically reach masses of tens to hundreds of solar masses. Medium seeds, formed from runaway stellar mergers in dense early star clusters, can reach masses of thousands of solar masses. Heavy seeds, formed through direct collapse, start at tens of thousands to hundreds of thousands of solar masses. Each category has observational signatures in principle. A direct collapse event in progress would produce a distinctive spectral signature, a hot, massive object with the spectral properties of a supermassive star rather than a galaxy or a mature black hole. It would be incredibly luminous for a very brief period, then transition to a more typical quasar-like signature as the collapse completed and accretion began. Nobody has ever captured this transition in observational data. The event is theoretically brief, lasting thousands of years at most, and occurs in the early universe where even Webb's sensitivity struggles at the faintest flux levels. The probability of catching a direct collapse event in real time in any given survey field is extraordinarily small. What observers have instead are candidate objects, systems at high redshift with unusual spectral properties that don't cleanly fit the category of a mature galaxy or a standard quasar. Some of these candidates show spectral signatures consistent with very massive, hot central objects with less surrounding stellar light than expected, potentially signaling an early-stage direct collapse product. Several were identified in Webb data within the first 2 years of the telescope's operation. None have been definitively confirmed as direct collapse black holes in formation. The confirmation requires ruling out alternative explanations. Obtaining high-quality spectroscopy across multiple wavelengths, and ideally catching temporal variability consistent with an ongoing collapse event. That process takes time and substantial observational resources. The stakes of finding a confirmed seed are enormous. A direct collapse event caught in progress would provide the first direct evidence for the formation mechanism of the most extreme early black holes. It would confirm or refute the theoretical models that have been built and tested on paper for 2 decades. It would transform a compelling theoretical explanation into an observed physical process. Until that happens, the seed remains hypothetical. The starting condition for the most massive early black holes is still an inference, drawn from the impossibility of explaining the growth any other way. Science frequently operates in this space, where the indirect evidence is overwhelming, but the direct evidence is missing. The history of astrophysics is full of phenomena confirmed indirectly decades before direct observation was possible. Black holes themselves were confirmed indirectly long before the first image of one was captured. The seeds will be found. The question is which telescope will be looking in the right place at the right moment. Before Webb delivered its first deep-field images, astronomers had a mental picture of what the earliest galaxies looked like. Primitive, small, irregular, diffuse collections of gas and young stars, without the organized structure of modern spiral or elliptical galaxies. Early galaxies were expected to be the rough, unpolished starting blocks from which the elegant structures of the modern universe would eventually be carved. Webb shattered that picture almost immediately. The earliest galaxies detected by Webb are far more structured, more luminous, and more massive than models predicted. Some appear to show organized disks. Some appear remarkably compact and dense. Many are brighter than the standard model predicted for galaxies of their age, suggesting either more stars or hotter, more massive stars than expected, or something else contributing to the luminosity entirely. The something else, in many cases, is almost certainly the central black hole. Active, feeding supermassive black holes in compact early host galaxies can contribute substantially to the total observed brightness of the system, making the galaxy appear more luminous and more structured than its stellar population alone would suggest. This creates an interpretation problem. When we measure an early galaxy's luminosity and infer its stellar mass, we may be significantly overestimating that mass if a bright central AN is contaminating the measurement. Conversely, when we measure its overall structure, the concentrated brightness of the central AN can make the galaxy appear more compact and organized than it truly is at its stellar component level. Separating the AN contribution from the stellar contribution in compact, high redshift systems requires resolution and spectral coverage that pushes even Webb to its limits. The work is ongoing. What emerges from the data, despite these uncertainties, is a picture of the early universe's galaxy population as more diverse, more mature-looking, and more influenced by central black holes than any pre-Webb model successfully predicted. The standard model's galaxy formation simulations consistently underproduced early massive galaxies, a discrepancy that became known informally as the impossible early galaxy problem within the community. The likely resolution involves both the central black holes and the formation efficiency of early stars. Population 3 stars and the first generation of metal-enriched stars that followed them were likely more massive and hotter on average than stars forming today, making early galaxies more luminous per unit stellar mass. Combined with AN contributions and possibly higher star formation efficiencies in dense early environments, the excess luminosity may be partially explained without requiring fundamentally new physics. But partially explained is not fully explained. The tension remains, and each Webb observing cycle produces new candidates that sit uncomfortably above even the revised predictions. The early universe keeps being stranger and more structured than the models that describe it. Science progresses through consensus, but it advances through conflict. The accumulation of early black holes and early galaxies that defy standard predictions has produced a genuine division in the cosmological community. On one side sit the defenders of the Lambda CDM framework, the standard model of cosmology, who argue that the apparent tensions can be resolved within the existing framework through better modeling of baryonic physics, more careful treatment of selection effects in surveys, and refinement of stellar population models for the early universe. On the other side, a growing group of researchers argues that the accumulation of anomalies is too systematic, too consistent in direction, and too large in magnitude to be papered over with incremental adjustments. They argue that the standard model needs structural revision, potentially including modifications to dark matter behavior in the early universe, changes to the assumed initial conditions for structure formation, or entirely new physics operating at cosmic scales. The disagreement is not merely academic. The standard model is the foundation of modern physical cosmology. Its predictions for cosmic microwave background power spectra, for baryon acoustic oscillations in galaxy clustering, for the large-scale geometry of the universe, match observations with precision that ranks among the greatest achievements in science. Abandoning or substantially revising it requires extraordinary evidence and a replacement that matches or exceeds its success across all those domains. Extraordinary evidence is arguably what Webb is beginning to provide, at least for the specific question of early structure formation. The tension between observed early massive galaxies and model predictions was quantified in multiple papers within Webb's first year of data, with some analyses finding discrepancies at confidence levels that would ordinarily trigger serious theoretical reconsideration. The defenders of the standard model point out, correctly, that systematic errors in observational measurements can mimic genuine tensions. High redshift photometric measurements are notoriously subject to contamination. Spectroscopic confirmations are time-consuming and incomplete. The full sample of impossible early galaxies has not been definitively confirmed through the rigorous spectroscopic follow-up required to rule out low redshift interlopers. The challengers point out, equally correctly, that the trend has held up through multiple independent analyses using different methods and different subsets of the data. Systematic errors don't typically produce clean, directional trends across multiple independent surveys. The debate will be resolved over the next decade as spectroscopic surveys confirm or fail to confirm the photometric candidates, and as new theoretical models are built and tested against the growing dataset. History suggests the resolution will be partial. Some of the tension will dissolve under more careful analysis, and some will require genuine theoretical advances. What is certain is that the field is more alive with productive conflict now than at any point in the past 20 years. That conflict, uncomfortable as it is how science advances from a working model to a truer one. The ancient black hole at 570 million years is incomprehensibly distant. 13 billion light-years of space separate us from it. Its host galaxy is long since transformed into something unrecognizable. The object itself has almost certainly grown far more massive, fed by billions of years of additional accretion and mergers. Yet its existence has a direct connection to the conditions that allowed Earth to form. The path is subtle, but it's real. The early universe that produced these extreme black holes was also the universe that built the first heavy elements. Population 3 stars, living and dying violently in the first few 100 million years, forged carbon, oxygen, nitrogen, iron, and dozens of other elements that didn't exist in the Big Bang's output of pure hydrogen and helium. Their deaths scattered those elements into the surrounding intergalactic medium. The active quasars, including the ancient system we've been studying, drove massive outflows that carried gas, and with it these newly forged elements across enormous distances. The jets and winds from feeding supermassive black holes in the early universe distributed chemically enriched material into the vast cosmic web, seeding regions that would later collapse into second and third generation galaxies with the raw ingredients of rocky planets and organic chemistry, without the early quasar feedback driving those outflows. The chemical enrichment of the intergalactic medium would have been slower, more localized, less efficient. Galaxy clusters that formed later might have assembled from gas poorer in heavy elements. The stars that formed in those clusters might have produced fewer rocky planets. The conditions for complex chemistry, and therefore life, might have been rarer. The solar system formed 4.5 billion years ago from a molecular cloud already enriched by multiple generations of stellar evolution and processed through the galaxy's chemical history. That chemical history was shaped in part by the energetic quasar activity of the universe's first billion years, including objects like the one at the center of this story. The carbon in your body was forged in a star. The iron in your blood was forged in a stellar explosion. But the galaxy that contained the molecular cloud that became your solar system was built in an environment chemically enriched by the outflows of ancient supermassive black holes that existed before most stars in the Milky Way were born. Trace the chain backward, and the ancient black hole at 570 million years is not a remote, irrelevant oddity. It is part of the causal sequence that produced the conditions for the Sun, the Earth, and everything on it. The universe's most violent early objects were, in a specific and traceable sense, part of the machinery that made life possible. That machinery is still being built and improved. The next generation of telescopes pursuing these objects will tell us how common that machinery was, and how much of what came later depended on getting it exactly right. Webb is already operating beyond what its designers considered guaranteed science. Its performance has exceeded expectations in sensitivity, stability, and longevity. And yet, for the questions raised by early black hole discoveries, it represents a beginning rather than an endpoint. The next generation of facilities being built and planned specifically addresses the gaps Webb leaves open. On the ground, 3 extremely large telescopes are in various stages of construction. The Extremely Large Telescope in Chile, with a primary mirror nearly 130 feet across, will offer spectroscopic capabilities that dwarf current instruments. Its ability to dissect the light of faint high redshift objects into detailed spectra will allow confirmation of the black hole masses, accretion rates, and host galaxy properties that Webb can only estimate from photometry and lower resolution spectroscopy. Spectroscopic confirmation at high redshift is the bottleneck slowing early black hole science. The Extremely Large Telescope breaks that bottleneck. In space, the planned Habitable Worlds Observatory will push into longer ultraviolet wavelengths, and the proposed Origin Space Telescope would extend sensitivity dramatically into the far infrared. Specifically designed to detect dust-obscured galaxies and active galactic nuclei across the universe's history. If the early universe's hidden population of obscured early black holes is as large as some models suggest, Origins class sensitivity would begin to reveal it. A particularly targeted future instrument is the proposed line intensity mapping experiments, which would detect the collective infrared emission of molecular gas across large cosmic volumes, mapping the density of star-forming and ang-hosting systems at high redshift statistically rather than individually. This approach trades the detail of individual object studies for the census power to map the full population. Most directly relevant to the seed question is the concept of a space-based mid-infrared survey telescope with significantly deeper sensitivity than Webb in the wavelength range where direct collapse candidate signatures appear. Such an instrument, though not yet approved for construction, would have the realistic potential to detect direct collapse black holes in their formation phase, catching the transition from collapsing gas cloud to active accretion in real time. If that detection happens, if a telescope catches a direct collapse event in progress at a redshift consistent with 500 million years after the Big Bang or earlier, it would be one of the defining moments in the history of astronomy, the confirmation of a predicted but never observed physical process, finally seen. That discovery would close one chapter of the story while opening another. Because a confirmed direct collapse event wouldn't just explain this black hole's origin, it would force a complete reconstruction of the early universe's history of massive object formation, with implications for every supermassive black hole in every galaxy that ever existed, including the 126,000 light-years from where you're standing right now. A supermassive black hole, 600 million times the mass of the Sun, fully formed at 570 million years after the Big Bang. Every tool we had said it shouldn't exist at that size at that age. Every model we trusted said there wasn't enough time. Every calculation said the physics wouldn't allow it. And yet there it is. Confirmed, reproducible, real. This is the specific flavor of discovery that reshapes scientific fields. Not the discovery of something new within a working framework, which science handles smoothly, but the discovery of something that breaks the framework itself, that sits outside the boundary of what the framework predicts and refuses to move. The response of the scientific community to this object and its growing family of early companions has followed the pattern that genuine paradigm challenges always produce. Initial disbelief, independent verification, incremental accommodation attempts, gradual recognition that accommodation isn't sufficient, and finally, the honest admission that something fundamental in the model needs to change. That final step is where early black hole science currently sits, not yet at consensus on what the new model looks like, but past the point of pretending the old one is sufficient. The productive question, the one that drives the next decade of research, is not whether the standard model needs revision for the early universe. That is essentially settled. The question is how deep the revision runs. Does it require only a new understanding of the first black hole seeds, a new formation mechanism inserted into an otherwise intact cosmological framework? Or does it require something more fundamental, a change to the properties of dark matter in the early universe, a modification of the initial conditions set by inflation, a new physical process operating at cosmic scales that current physics doesn't contain? The history of science is filled with moments that felt like the end of a framework but turned out to be its expansion. Quantum mechanics didn't destroy classical physics. It revealed the regime where classical physics is an approximation of a deeper truth. Relativity didn't eliminate Newtonian gravity. It revealed the conditions under which Newtonian gravity is a limiting case of something richer. The discovery of this ancient black hole may be that kind of moment. A confirmation that our cosmological framework, as powerful as it is an approximation of a deeper, stranger truth about how the universe builds its largest structures. And the strangest part of all of this is the question it leaves open at the edge of everything we know. If a supermassive black hole can form and reach 600 million solar masses in 570 million years, what else happened in that compressed, violent, poorly understood early era that we haven't found yet? What other structures, what other objects, what other processes operated in the universe's first moments that our models never predicted and our telescopes have never reached? The universe built something impossible before it had finished setting its own rules. We are still figuring out what the rules actually are, and every answer we find points at a larger question just beyond the edge of what we can see.